So hi everyone, I'm very excited to be here today. I came here all the way from Israel to tell you a little bit about how we do data science at Bluevine, which is actually an American company, but our R&D is based on Israel. So let's start. My talk would be composed of two parts. The first part would be the story of a model I worked on at my job at Bluevine, and how I had some problem with this model, how I found a solution for the problem, and also how we do continuous model training in production. And the second part, which is very related to the first part you would see, I will describe a model explanation framework called LIME, which was developed by a research group from Washington University, which I think it's really amazing. And we will see how everything connects here. So let's start with the first part, the story of a model. I was asked to build a model for returning client and debtors. Now, what is a client and what is a debtor, and what does Bluevine does anyway? So for you to understand better what I'm talking about, I prepared a really short movie that explained it very nicely.
You're a small business owner. Maybe you're the CEO of a marketing agency, or you're an engineering consultant. You might even tame elephants for a living. But no matter what you do, it often seems like what you end up doing most is waiting. Yes, waiting to get your invoices paid. Waiting and waiting and waiting. These cash flow gaps make it hard to manage expenses. Also, if you could get the money now, you could reinvest it in growing your business. Now you can. Introducing Bluevine, a fast and easy way to get an advance on your invoices. Signing up with Bluevine is easy. Enter a few details about yourself and your business, and connect your invoicing or accounting software. Your unpaid invoices will automatically appear in your dashboard. Select one or more invoices to advance with a click of a button. You can get cash in as little as 24 hours for your first invoice advance, and even sooner for repeat usage. So how does your customer pay Bluevine when the invoice is due? Once you're approved on Bluevine, you'll receive a Bluevine account, a unique bank account number, and a physical P.O. Box address, both in your business name. With the bank account number, you will be able to accept electronic payments, and with your P.O. Box, checks. And since your Bluevine account is in your name, your customers can continue making the payments in your name. Sign up with Bluevine, stop waiting, and free up your cash today. Bluevine, fast funding. Simple and transparent, 100% online.
Okay, so now you understand a little bit what Bluevine does. What we actually do is help small businesses funding. For example, if you are an exterminator, you have a business of exterminating bugs, and a law firm comes to you and asks you to do a job for them. You come to their offices, you exterminate all the bugs, but in the end you don't get paid on the spot. You get paid maybe in the end of 30 days or 60 days or 90 days, and you get the invoice. What you can do in order to get your money, because you need to invest in marketing or in buying equipment or paying your workers, you can come to Bluevine, you give us your invoice, and we give you an advance on your invoice. And in the end of the 30 days or 60 days or 90 days, the law firm would pay directly to us the amount of money it owes you. So this is our business. In this scenario, the client is you, the exterminator, Bluevine client, and the client of the client, the law firm, is the debtor. And this whole scenario is called a deal for us. That's how we treat it, an invoice factoring deal. I was asked to build a model to automatically approve these kind of deals for returning clients and returning debtors, meaning that these are clients that we already had deals with them before. So it should be really fast. That's why we need a model. So it would say automatically yes or no, instead of an analyst trying to analyze all the data and understand whether this is a good deal or a bad deal, right? So since this is a deal of a client that we have history with, we have different kind of features. We have features of the client, of the history of his payments, and all kinds of information we gather on the client, and also features of the debtor, history of the debtor, and his deals with us. In addition, we have features of the deal itself, the deal amount, the deal due date, all kinds of things. So for example, my data frame would look something like this. I would gather data for all of my deals, all of the deals I have in my sister. And for each of them, I will find by the specific point in time of the deal, all of the relevant features. For example, client negative web appearances, meaning how many negative web appearances the client had or we saw. Debtor average invoices amount from the history with us, and deal duration days, all kinds of features. And the target is to predict whether the deal is good or bad. A deal is good is whether it was approved and paid on terms. A deal is bad is whether it was rejected by us before or it was approved but was not paid on time. So I have more and more features like this. And the problem is that some of them are numerical, some of them categorical, some of them are binary. And some of the machine learning models I know assume some distribution of my features. For example, they assume that all the features are normally distributed or Bernoulli distributed, and they're not suitable for this kind of data. So in order to use these kind of models, I have to do something. I have to maybe change my data, make all the numerical features binary features, for example. Or maybe I should change the model to treat differently different types of features. All of this is very hard work. Something else you can do is just use a tree-based model. And why a tree-based model, such as decision tree or random forest? Because tree models that treats the numerical features and the binary features the same. They do splits on values of the features. They don't have any assumptions on the underlying distribution of the features. That's why they're so suitable here. And I have a full slide on this that we like so much random forest. I mean, I could use just a decision tree classifier. But decision tree classifier, although it has this nice property that it works well with a mixture of feature types, it has another problem that it tends to overfit, and it has a high variance, which caused a high classification error. In order to deal with that, you can use an ensemble of trees, a group of many, many trees that does the decision together. This kind of ensemble is a random forest. Random forest is an ensemble of trees that were trained on different subsets of the features of the data and also different parts of the data, which cause each of the trees to be a little different. So in the end, when you average all of the results, you get a low variance model, meaning a lower error model, more robust. That's why we like random forest so much. In addition, it has a way to capture the relation between different features. For example, if you use a linear model, it gives a weight to each of the features in separs, but it doesn't capture relation between different features. In random forest, the resulting function is just a combination of all the features, different combinations of rules. So you have the ability to capture a very complex relation between features. Another issue I had with my data is that it's unbalanced. As you probably heard from fraud detection problem, we usually have this problem. We had only 3% bad deals, which is very little. We need to address that when we build our model. We can oversample the minority class, for example, or we can undersample the majority class. We can do all sorts of things, but we need to think about this and watch this. And then what I did was just, okay, I have a data. I knew that it was a nice data. We had a model working from before, like a year before I wrote it, and we just wanted to write a new version with all of the new features we added, and we knew we had more data, and we decided to just try a model. So I did 10-fold cross-validation to verify I have no overfitting. And this is the result I got. This is, for those of you who are not familiar, this is a ROC curve. And what we see here in green is the ROC curve of the old model we had. And in blue, we see the ROC curve of the new model. And what we see here is amazing, because the ROC curve, it's in the x-axis, you see the false positive rate, and the y-axis is the true positive rate. For here, for example, if you look at the top left corner, you see that for a true positive rate of about 95%, you get a false positive rate of about 5%, which is truly amazing. I mean, I can just go home. You know, Tel Aviv has a really nice beach. You can just go to the beach of Tel Aviv, relax, and let the model do its work, right? What do you think? I can? Well, probably not, because then the lecture would be ending here. So as a data scientist, I know I have to be very, very skeptical. And if I just see automatically this, I'm skeptical. Something here is not working correctly. So I decided to dig deeper into my model and understand what is going on. Why do I get such amazing results? Because this is unreal. You don't see these kind of results usually on real data. So what I decided to do is to look at the feature importance of the model. And the feature importance is the estimation of the reduction of accuracy if you remove a feature from your model. So the first feature is the most important and in decreasing order. And I expected to see something weird here. Maybe some feature is very, very strong, stronger than all the others, and then it might be some data leakage or something like that, some data which is not supposed to be in my data set. Or maybe, I don't know, something should have been weird here. But I looked, and everything seemed pretty much OK. I mean, these are features that I would expect that would be important for this model. Client bad history too, client payment history, client income, deal amount, debt or funding history. These are all very logical features to be in this kind of model. So I said, let's try something else. I have many, many features. Let's just select the 10 best features and try to retrain the model only with these features. Maybe that will light something in a different light. And then I got this rock. Still amazing. Yeah. So I said, well, let's try something else. Let's then take the 10 worst feature. Maybe here the picture will be a bit different. And still, really nice results. What is this? What's going on here? So I said, OK, let's make it very, very simple. Let's just take the 2 best features. And this is what I got. Still a really nice model, only with 2 features. So I said, let's go in a different direction. If I take only the 2 best features, it must be a pretty simple model. Now, I know that I use scikit-learn, and I know that there's an option with GraphViz to visualize the tree. So I said, let's look at the tree. Maybe I will understand something from that. This is the tree I got. I remind you, this is from 2 features alone. It's really hard to understand. Even on this really big screen, it's really hard to understand what's going on here. It's just a really, really huge tree. But what I do feel when I see this tree is that it seems like the model is learning specific values. It seems like there are many, many leaves. So this many, many leaves on only 2 features, it feels like it's learning many, many specific numerical values. Well, this is not good. I mean, it seems like overfitting, right? Is this really overfitting? Let's remind ourselves what is overfitting. Overfitting occurs when the model is memorizing the training data instead of generalizing from the trend. But I did everything correctly. I mean, I took certain deals for training and certain deals for testing, different deals. So I'm not supposed to see overfitting, right? So what could be the problem? Do any of you have an idea What could be the problem here? Yes? Because what? I used of the minority class? I actually didn't do it. I didn't use. I just tried without. I really went simple. But that's an idea. Anyone other idea? Yes?
That the cases you took for the outer sample, while there were different transactions, so to speak, but the same individuals who appeared earlier on.
That's very right. Did you see the presentation on YouTube? We already have it on YouTube. OK, so he has a point, the gentleman here. So what I tried to do in order to understand whether this is really the problem, I tried to simulate the future in a different way. We didn't talk about it, but as the gentleman said, our clients make multiple deals with us, meaning that our data set, it holds many deals that might be from the same clients. I mean, certain deals could be from the same client. It's not all from different clients. So what I try to do now is, instead of just randomly dividing to train and test, I trained the model on deals from certain clients and tested the model on deals from other clients. Okay, now I don't have any overlap in the clients between the train and the test. And let's see what the result I got then. Really bad results. And I said, oh no, I want my beautiful rock back. Come on, what's going on? But it was really sad because I started to like these nice results. I never had these kind of results. But this led me to believe that this is really the problem, that the models somehow get messed up because I have deals from the same client. And instead of learning what is a good deal, it just learned to recognize specific clients. Now, let's see if that's really correct. So, as I said, maybe the classifier is memorizing the good clients. To understand if that's true, I wanted to check a few things. First of all, how many deals per client do I have in my data? Do I really have so many deals per client in my data? And second of all, is the client behavior consistent? I mean, is each client only have good deals or only bad deals? Otherwise, this wouldn't work, right? So let's try it out. And the third is, how similar are deals from the same client? Can the model really recognize two different deals are from the same client? So let's see the results of these checks. So first of all, this is a histogram of a deal per client count. It shows the number of deals per client. And we see a peak here. It's not around 1. It's a bit more than 1. And in the end, what's important is that 90% of my clients, the clients in the data, has more than one deal. So yes, it's probably possible to learn to recognize the clients if we have, for most of the clients, large part of the clients, we have a few deals in the data. And second of all, I wanted to check, is the client behavior consistent? So I checked what is the rate of good deals per client. And I saw that for 75% of my clients, they only have good deals. They're not a mixture, only good. For 10%, they only have bad deals. So 85% of my data is very consistent. So if the model can recognize two deals are from the same client, it can classify them the same just because the model recognized this is a specific client, instead of understanding what is the pattern of a good deal. So then I tried to understand how similar are deals from the same client. I took a random sample of my data and checked the similarity values between the different deals. So the diagonal here is the same deal, so it's in strong purple. And the light purple is low similarity. And for example, I can see the deal 3 is highly correlated with deal 2 because they are both from client 3. But for example, deal 3 is not correlated with deal 1 because they are from different clients. So for a random sample of the data, this was true. I saw that deals from the same client are highly similar. But I wanted to understand how to check this for my whole data set. So what I did is for each deal, I tried to find the most similar deal in my data and measure the value of similarity. Then I took all these values of similarity and did a histogram. And what I got is this histogram. The similarity is 0 for no similarity and 1 if it's very high similarity. And as you can see, there's a high peak around 1, meaning that most of the deal has at least one deal which is very, very similar to them, which correspond to my former results that 90% of the client has more than one deal in my data. So deals from the same client are similar. This is the conclusion. Also, a large portion of my features are client features, which makes it easier to recognize the clients in the deal. So my conclusion was when the classifier gets many deals from the same clients, it just learns the wrong thing. It learns to recognize the client instead of understanding what is a good deal and how does a good deal look like. Any ideas how I can solve this issue? Okay. Oh, yeah. Okay, that's an idea, but then I will lose a lot of valuable information. Because I want the model to use the client feature, just not in a way it does. You understand? I wanted to look at it not to recognize the specific lines, but to use it along with the other feature to understand a pattern. So I didn't do that. Any other? Okay, so. I didn't get the beginning. Can you repeat? I'm not sure I understood, but maybe it's similar to what I did in the end. So let's see. What I did is just, instead of using all my data, just use a part of my data. Sample one deal per client. This will prevent from the model to recognize a client because it will only have one deal per client. It wouldn't have many deals per client. Now the model would understand what is a good deal and not search for specific client values. And if I look at the previous plot we saw of maximum similarity between deals, and now I do the same histogram on my new data set of one deal per client, I see that I get this red line. This red line means that deals are not similar to one another in my new data set. The data set is decorrelated, okay? So in this new data set, I get a much smaller sample size because, as I said, I had many deals per client, and now I just sample one deal per client. So I lose a lot of information. So what I did in order to solve this problem is instead of just sampling one deal per client and building a model based on that, I did it a few times. I created one data set with one deal per client, and another data set with different deal per client, and another data set with different deal per client. And for each of these data sets, I created models, and then the final result is an ensemble of these models. And this is a nice graph that shows that. You see I have the correlated data sets and models built based on them. And the final model is an ensemble, some vote of all of these models. And let's see some results. So these are the results of the rock curves, and on each of them, I add another model and another model. And as you can see, there's a slight increase when I add more models to the ensemble, but not very large. And I wasn't that satisfied of the result. I mean, rock 70 is nice, but it's not that good. So I said, let's try maybe a different model now. I mean, I know this works okay, but let's try something else. This was all with random forest. And as I said, I really like trees. It worked well with my data. So instead of using random forest, I used something else. Anyone have an idea what it was? Something similar? Right, XGBoost. XGBoost is a Kaggle champion. You can find it now in all of the latest, late few years, I think. It was a part of any of the winning solution of Kaggle competitions. And I heard about it, and I tried it. And I said, let's see if it works well with my data. And these are the results I got with XGBoost. Much nicer. From rock of 70, I got now rock of 77, which is really nice. I can go to production now with my new model, with Ensemble, with XGBoost. But now I just had a little last problem I wanted to deal with. How usually people do machine learning in production is that they train the models offline, and then they do the prediction online, of course. But in our scenario, and in many other scenarios, the world is not stationary. The world keeps on changing. The people change, our policies change, and we want the model to keep on learning, to keep on updating. So what we developed is a framework for continuous model training. And each time, this framework runs every week, reads all the new data, and forgets all the too old data, and retrains the model automatically. And if the model is good enough in the metrics we define, it deploys the new model to production. And this is the new model DAO that's being used all the time. So this prevents from the old model from degrading, and also keeps us updated on what's going on all the time. So that's it for continuous model training. Do you have any questions on part 1? Yes?
I have a question. So why you told me that this is based on my understanding. So you just use one deal per person, and you then use different data set. Why you, like, for example, took the same person and get the average of the whole deals and use that? Why you didn't use that?
That's an idea, but I think the average will lose a lot of information because the average is not a real deal. I mean, if the person had a deal of $10,000 and a deal of $500, and I take the average, this is not something real, you see? So it's not really a linear thing to just average all the features here. There are relations between the features which are not linear, and if you just average them, you will lose these kind of connections.
I think, as you said before, you have more than 85% consistency, right?
Yeah.
So sometimes I guess you can use that average because your data is more consistent than other data that I was working with. So I think there is a possibility that
maybe not the average. Maybe just select one of the deals per client in a more smart way than random. Maybe just do clustering. I actually thought about it afterward. Just cluster the deal per client and try to choose the most representative deal per client. That's a possibility. Maybe we'll do it in future versions. Thank you. Yes?
Since you're generating multiple models with the one deal per client, aren't you oversampling the clients that only have one deal in your data set?
Yes. But there are not so many. But that's right, yes. Yes.
So, multiple deals per client, were there any time dependencies? So was there a case that maybe a client had 5 deals but over a period of, say, 6 years, right? In which case your original question about, your policies change, the environment change, that itself gets featured into your various models.
That's right. That's why I chose it randomly. I didn't want any dependency on time. Other thing is that we only exist about 3 years, so we don't have 6 years of data. I didn't have that much data. I also just took the data of the last year in order to prevent these kind of changes of policies. but good idea. Yeah. Yes.
How quickly over time do feature affordances evolve? Is it just stationary or has it been moving?
That's really interesting. I need to check it out. It's kind of new, this thing, but it's interesting to track that, actually. Along with the continuous model training, I also added some framework for model performance that we track the model performance over time. But I don't have enough data to answer to that question, but that's very interesting to see whether the feature importance change. I like it. Okay, so we'll continue now, and we'll have more questions in the end if you want. The second part is I wanted to talk to you about Lime, model explanations by Lime. This framework helps us understand what is inside the black box. Now, as I said, this is very related to the first part, because the first part we saw a model in the beginning that was perfectly, that had perfect results on the validation data, but in fact, it didn't learn the right thing. It was a bad model. It didn't help me at all. And I tried to dig and find a way to understand what is the problem. Now, this kind of framework can help us understand whether our model is reasonable and learning the right things. Like, as you all know, the machine learning models we usually use are really complicated. It's really hard to understand what they really do. We just take the results, we look at the validation, and we say, OK, it works well, validation, so we believe in it. So this is something that can help us dig deeper into our model and understand whether it's reasonable or not. And to understand how it works, we will start with an example of data leakage. I took it from the Lime article, the Lime paper. And I'm very happy they did this example because it gave me a reason to put a nice photo of dogs in my presentation. So as you can see, they're really nice. This is a wolf, and this is the beautiful husky dogs. And what they tried to do in this paper was to show an example of data leakage. And how did they do that? They took a pre-trained network, I think it was Google Inception network, and transfer learning. The network was already trained on photos, and now they gave it, they retrained the last layers, and they gave it photos of the husky dogs and the wolves, and they trained the network, and they got perfect results. But they didn't just give it photos of husky dogs and wolves. All the photos of the wolves had snow in the background, and all the photos of the husky dog did not have snow in the background, okay? And then they gave this trained network a photo of a husky dog with snow in the background, and of course, it was classified as a wolf. And then they applied Lime on it. Lime gives you the pixels which were most influential in this decision of the classifier, meaning when the classifier decided this husky is a wolf, which were the pixels that he looks at that made him made him have this decision. So here, as you can see, the explanation is not the face of the wolf, it's the snow in the background, because the classifier learned to recognize that when he gets a wolf, it always has snow in the background. So now when he gets a husky dog with snow in the background, it has to be a wolf, right? Well, this is not like that in real life, as you know. And this is what means data leakage, and a nice example of how you can detect it with Lime. So just the formal definition of data leakage is when unexpected additional information is in our data, which will not be there on real life. And this just ruins our model because it makes the model learn the wrong thing. Instead of learning the face, the difference in the faces in the body of the dogs and the wolves, it just learns the background. And so it didn't understand the right patterns at all. Another nice example of Lime, this was an example of how Lime can show us when the model is wrong, is not doing the right thing. Now this is an example of how Lime can show us a model is reasonable and is learn the right thing. So they took a photo of a dog, a Labrador, playing acoustic guitar, and they gave it to the same Google Inception network. And what the network said, it returns 3 classifications of what it detects in the photo. And the first one was electric guitar, which is not in the photo. Okay, as you can see here, the pixel that explains the electric guitar is this. It's the part of the acoustic guitar that actually looks like an electric guitar. So this is a wrong classification, but the explanation makes sense. Okay? So the second prediction it gave is an acoustic guitar, which is correct. And also you see the pixels that explain that are the part of the pictures that shows us the acoustic guitar. And the third prediction was a Labrador. And the explanation is there a Labrador face. So this totally makes sense. I mean, prediction is not perfectly accurate, but the explanation makes sense. So this helps us believe that this classifier is good. So these are the 2 main usage for Lime, to understand whether a model is reasonable and to understand whether a model is bad. And I just wanted to say that I heard about Lime when listening to the Data Skeptic podcast. If you don't know it, I really recommend. It's really nice. And I just wanted to give them the credit. And a bit about how it works. I really like the mechanism behind it. What it does, as we said, it gives explanation for a specific sample we want to explain, for a specific photo or a specific sample or anything. And how it does it, it's a little bit hard to see. But this photo shows some feature space with a very complex decision border between 2 classes. The classes are the circles and the pluses. Okay, and the decision border is very complex, it's nonlinear, and the final model resulting is nonlinear model is very complex and it's hard to understand it. So what the Lime people did, they took for a specific sample, they tried to approximate the model in the area of this sample and do a linear approximation of the model in this area. Now when you get a linear approximation of the model, you can give an interpretation of the model because you have coefficients of the new linear model you got. And using these coefficients, you can understand which features were the most important for the decision of this sample. So what they did, they just, for this specific sample they wanted to explain this plus, they generated similar samples in the area of it just by adding noise to this sample. They created predictions for the, they create a prediction for this neighbor sample, and then they create an estimation of the complex model by a linear model. And from that, they can get the most important features for this specific sample prediction. So I wanted to apply Lime to close the loop. I want to apply Lime on my model, on the initial model and on the final model, and to see whether I saw hints, because I found out about Lime just after I had this problem with my model. So I wanted to see whether I would see any difference between the explanation when I would see something weird. So how can you apply Lime? It's very easy. You just to pip install Lime, and then you import it, and you get, you create an explainer object, and you give it your data and your model and your features, and it's very easy. It's all open source and online. And then you create the explanations. Now the explanation can be generated as text and also as HTML, as you see above. This is the HTML they give. You can show it in the IPython notebook. And it shows you the bad and good columns. In my model, I had good deals and bad deals. And here I applied Lime on a specific deal, which was a bad deal. And I applied it on my initial model, the one that learned the clients and not the patterns of the deal. And what I saw is that it said that all the features, the primary features, said that this deal is bad. And it tells you which values in this feature are the values that said that this is bad. And this is another visualization I added. They don't have it in Lime. I just created it myself. It just shows you the ranges of the values which was most important for this specific deal. So for example, the client bad history, if it's larger than 0, then it's bad. If I had good ones, then it would have been in blue. The fact that deal history sum is larger than 4,000, it's bad. Now you can't understand much of this, but what you can see is that there are some very specific values that are important here. For example, if client history 1 is between 1,000 and 2,000, it seems pretty specific to me. Pretty hard to understand without knowing all the context, but that's what I saw here that was interesting. Also, there are pretty many client features which are the most important, but that is the main thing I saw, and that all the features are considered as bad. Now, I applied the same with the same sample. I applied Lime on the final model, one of the models from the ensemble. I didn't use all of them together. And this is the result I got, the explanation of Lime for this. And here, first of all, not all of the features are bad. There is also one good feature, which is a more balanced picture. In addition, you can see here that there are not specific values. I mean, 0 is not a specific value. It's like pretty, it's logical. It's not very, between 1,000 and between 2,000. And so since I have more general decisions here and not specific, I feel like this is a better model. So that's what Lime helps me understand here, that I don't learn specific values, but wider ranges of values, and this is why the final model learns the right thing, not like the initial model. So to summarize, in the beginning we saw a model with perfect validation result that actually memorizes the clients instead of understanding what is a good deal. We saw a solution for this problem by ensembling different models learned on decorrelated data sets with only one deal per client. Afterwards, we saw how we can deal with the fact that the world keeps on changing by keep on updating our models in production. And in the end, we saw a really nice explanation framework that can help us understand whether our model is learning the right things. And I just want to add that after that, I added Lime to all of our, we added Lime to many of our models in order to help us and our analysts understand the decision of our models afterwards. And it's been very useful, so I like it. And that's it. Questions? Yes?